Okay, just want to talk about independence and what independent events are. So an independent event is when you have two events and basically they stand independently of each other, so they don't affect each other. So they're independent of each other. The example of things that are independent would be like if you threw a coin and a dice. Okay, so throwing a coin, if you want the probability of getting a head and 6, a coin's 1 on 2, getting a 6 would be 1 on 6. One does not affect the other. It doesn't matter what you get on the coin, that doesn't affect what you get on the dice. You could do 2 coins, you could do 100 coins. If you threw 100 coins, what you get on the first coin doesn't impact what you get on the last coin. Something that would impact or that wouldn't be independent of each other would be if you did something without replacement. So if you drew something from a bag, then you did it without replacement. So the second probability is impacted by what happened on the first. For example, you've got 3 red, 4 blue balls, and you want to get the probability of a red and a red. Okay, so it's 3 on 7 times 2 on 6. So the second one was impacted by what happened on the first. If you replaced it, then it would be the same probability and not going to have an impact on each other. Now, I just want to go into how to prove something is independent. Then the probability of A and B happening will be the same as the probability of multiplying the probabilities. Probability of A times the probability of B. Now, there's a few formulas I just want to make sure that you're familiar with. So the probability of A and B happening is the probability of A times the probability of B. We also know this one now. The probability of A given B is the probability of A and B happening over the probability of B, and the probability of A union B would be the probability of A plus the probability of B minus the probability of them both happening together. So it's minus the intersection. So if that's A and B, then you add the two things. So you do A and then you do B, and then you have to minus the intersection. That's the point that's inside there, where they both happen, because you don't want to count the intersection twice. Okay, now we're going to use these, but I just want to show you when you go to prove that when something's independent, you just have to show that that rule works. Now, I just want to show you why that would prove that something is independent. Okay, so if you look at probability of A given B, okay, then we're looking at, given that B happens, is this actually going to affect A at all? So the rule for that is probability of A and B happening together over the probability of B. Now, if you can split those up and make the probability of A and B the probability of A times the probability of B, then what you'll realise here is that these two things cancel, and then you end up just with the probability of A. So what is this actually saying in a mathematical sense? Is that given B, what's the probability of A? Well, the probability of A is just A. So that's actually showing independence. So that's showing that B, that's telling you that A is not affected, and it's not affected by what happens by B. Okay, it stands alone. It has its own probability. All right, so we're just going to look at a few questions where we've got to actually find a few things. So I'll look at this one here. Okay, so looking at the first one, we want to find, first of all, the probability of A and B. So the probability of A and B is the probability of A times the probability of B. So, because that means end, so it's going to be 0.6 times 0.35. That will be the probability of A. Actually, that'll only be if A and B are independent, and we don't know exactly that they are. So we've got the probability of B given A. That's going to be equal to the probability of A and B happening over the probability of A, because it's B given A. So that means that the probability of A and B will equal the probability of B given A times the probability of A. Now the probability of A is just 0.6, and the probability of B given A is 0.5. So that's the probability of A intersection B happening. So that's going to equal 0.3. Okay, if you look at the second one, so the probability of A given B, so instead of B given A, it's A given B, is A intersection B over the probability of B. So that means it's 0.3 over the probability of B, which is 0.35. So that's 30 on 35, 6 on 7. Okay. All right, so let's look at the next one. So the next one states, that's B. So we want to find, for the second one, the probability of A intersection B. Okay, now we have probability of A union B. So the probability of A union B is the probability of A plus the probability of B minus the probability of A and B happening, or intersecting B. So if we now look at that, to move this over to that side and that one there, then the probability of A and B happening is the probability of A plus the probability of B minus the probability of A union B. So all we need are those values now. So probability of A is 0.7, probability of B is 0.4, minus the probability of A minus the probability of A union B, which is 0.8. So this ends up being 0.3 altogether. Okay, and now this one here, we can make that the probability of A and B over the probability of B. So we just found that was 0.3, and the probability of B is 0.4. So it's just going to be 3 on 4. Okay, C. The probability of A and B happening. All right, so we have the probability of A given B is the probability of A and B over the probability of B. So let's just get rid of this. So I got a little bit of space to work out. So the probability of A given B would be, that's 0.8, equals the probability of A and B over the probability of B, which is 0.4. So A and B happening is 0.32, because you times that up there. And the probability of B given A is the probability of A and B, but it's over the probability of A, which is 0.6. So it's 0.32, 0.6, which is 32 on 60, which is 16 on 30, 8 on 15. That's the solution. Okay, so I just want to look at these questions. So the first one, I'll just do this part here. So we want to determine whether they are independent or not independent. So the probability of X intersection Y has to equal the probability of X times the probability of Y. All right, so the probability of X intersection Y is 0.06. And the probability of X times the probability of Y would be 0.2 times 0.6, which is 0.12, and these are not equal, so no, part one's not independent. When we go to 3, probability of X times the probability of Y would be 0.2 times 0.3, which is 0.06. And you can see that that is the same as that. So therefore the second one, yes, it is independent. Okay, now part B, we want to prove that, we want to show that these are independent. Okay, so we've got this though. And so that equals the probability of A plus the probability of B minus the probability of A intersection B. So to prove it's independent, we really need to be able to find this, and then we need to be able to multiply the 0.6 and the 0.45 together. So the probability of A times the probability of B equals 0.6 times 0.45. So it's just 0.6 times 0.45, which is 0.27. And then if we look at the other part, probability of A and B happening together, you can actually find the probability of A intersection B by solving for this one here. And so that's A union B minus probability, that'll be minus, plus the probability of A plus the probability of B. So A union B, so what's that actually equal to? 0.78. It was a bit small there. So that's going to be minus 7.78 plus the probability of A. So what's the probability of A is 0.6 plus the probability of B, which is 0.45. So you have minus 0.78 plus 0.6 plus 0.45. It's 0.27, which is the same as what we got before. Okay, just going to look at this two-way table and then independence. So find the probability that the female has a license. So where's the female with a license? That would be 30 out of the total 100. A male has a license. So a male has a license, that'd be 45 out of 100. Okay. Find the probability that a randomly selected person who has a license is male. So if they have a license, the chance that they will be male would be 45 on 75. Person who has a license is female. So have a license is female. That would be 30 on 75. According to the data, is having the driver's license dependent on gender? Well, I guess to have a look at this, you have the probability that they have a license given they're female and the probability that they have a license given they're male. So the probability they have a license given that they are female, if they're female and have a license, that would be 30 on 40, so it's about 75%. Probability that they have a license given that they are male. So given they are male, that'd be 45 on 60, so that's about 75%. So no, it's not dependent on it, because you get the same percentage for having a license whether you're male or female.